Hello everyone, I'm Xinqi Zhu from the University of Sydney. In this work, we will introduce an unsupervised disentangled representation learning method using group structures. In traditional disentangled representation learning, we encode an image as a vector. When the image changes by a certain semantics, we expect the latent representation to vary along a single dimension. Usually, the embedded sample is moved along a latent direction. When changing by another semantics, the latent code will change along a different dimension, which is orthogonal to the previous one. We may usually view this change as moving an embedded sample point along different latent directions. However, we can also view these changes as translation on the latent space along different directions. Here, let the blue square represent the whole latent space. The embedding of the image can be seen as moving the whole latent space from the origin to the point of 0.3, 0.7. And when we change the image by some semantics, the latent space will be translated along a direction in the latent space. When the image changes another semantics, the latent space will be translated along a different dimension. The interesting point is that now the data variations are equivariantly represented by translation in the latent space. It may feel a little meaningless by just reinterpreting the latent code change from another perspective, but it actually provides us with possibility to expand our imagination. For example, we can ask ourselves, why do we only use the translation to transform the latent space? What if other types of transformations are used? Here, we show an example using other transformations. Imagine we have an embedding that describes the state of the latent space. How this embedding is defined will be introduced later. Now we just need to remember this embedding represents a state of the latent space. When the image changes by some semantics, we can now use a certain type of transformation to act on this latent space. For example, we can rotate the space by some degrees. For another semantic change, we will use another type of transformation to act on this space. Here we show an example of scaling transformation. These transformations are clearly different. In this case, we distinguish the two semantic changes by two types of transformation on the latent space. Here we show a brief comparison between the old fashion of disentanglement and our new fashion. For the old one, the semantic changes are represented by both translations but along different latent directions. For the new one, the semantic changes are represented by different types of transformation. Now you may ask, okay, it looks cool, but why do we need the new fashion? The key difference we consider is that in the old fashion, we use a fixed and predefined transformation, which are translations along different latent directions. But in the new fashion, we can set these transformations to be learned adaptively. The hypothesis behind this potential improvement is that we expect the equivariance between the data variation and the latent transformation to be more easily achieved if the used latent transformation structure is adaptive rather than fixed. This idea is conceptually expressed in the following figure. On the left, we show the variations in the data space, and on the right-hand side, we show the transformations in the latent space. In the old fashion, a learning method needs to learn the equivariance on the fixed latent structure, while in the new one, the method can update the latent structure to fit the data variation. And we assume the new scheme is an easier task than the old one. In this work, we use a learnable group structure to achieve this goal. and we only consider continuous matrix groups for easier parameterization and computation. Here we give a very brief introduction about how the groups are going to work in our paper. We call this equation where we take a step of transformation and representation. The term G, which denotes the transformation, is a group element. We can expand this equation as an example in this way, where the representation are vectors, while the transformation group element is an invertible matrix. In this example, the group element G is trying to rotate the latent space. We can also show the other example here of the scaling. You can see in this case, the group element G actually maps a vector space to itself. But we need to remember that the group element doesn't necessarily need to act on a vector space. It can actually work on a group structure as well, like shown here. In this case, the group element maps a group structure to itself. It is a very useful property and will be used later in our modeling. Let's look at this example again. We now can see the actions G1 and G2 are different group elements, but now the problem becomes how do we define this embedding or representation function? In this work, we assume there exists a canonical sample x0, and every other sample can be transformed from this canonical one through group transformations in the latent space. When we apply a new group action on an example, the action can be absorbed into transformation term, which will maintain the transformation structure from the canonical example. From this modeling, we can see it is the group G that defines the whole representation structure, and the canonical embedding sigma x0 can actually be seen as a constant. An interesting point is that we propose in this work to set this canonical embedding to be a special fixed value, the group identity element E. And we will use the following formula to do the representation. As we can see, now the samples are embedded on a group structure, and we name this embedding as the group representation. Before moving on, we show a brief summary here. Now we encode an input image by a group representation. When a semantic change occurs, we expect a corresponding group element can act on the current representation. For another semantic change, an element on another group will act on this representation. As there is an equivariance between the data and the representation, the encoding of the varied input will be the transformed representation. It looks like the two semantic changes have been disentangled into G1 and G2, which looks cool. But how do we disentangle the original group representation, the sigma x? In our modeling, we expect the group representation to be a composition of multiple subgroups, with each subgroup representing a single disentangled semantic meaning. When a new semantic change occurs, the new group action will be absorbed by the subgroup that represents this semantic meaning. In this case, the disentanglement on the group representation is actually achieved via this subgroup decomposition. Now, the next question is how to learn such a decomposable group representation in practice. As we want a representation to be a group structure, at least we need a way to obtain elements on a group. Usually, a group is a set of invertible matrices, and they cannot be directly located via general optimization method in a vector space because we cannot guarantee their invertibility. In this work, we focus on Lie groups, and we can adopt the Lie algebra parameterization to help us learn a Lie group. The parameterization is shown here. The matrix exponential mapping can map an arbitrary matrix A to a group element. The matrix A is represented by a summation of m components. Here, the Ti's are scalars and Ai's are matrices. You can see that the second equation actually forms a vector space with Ai's being the basis and the Ti's being the coordinates. In this form, a group G is defined through a vector space A, which is called the corresponding Lie algebra. As A is a vector space, we can now do general optimization such as SGD on this space. We can view this basis A as learnable weights in a deep model as it determines the structure of the group. To achieve the subgroup decomposition we mentioned earlier using the Lie algebra parameterization, in this work, we would like to enforce a straightforward decomposition, namely one parameter subgroup decomposition. In this case, each subgroup is parameterized by a single basis component, AI, and a single coordinate Ti, representing a single semantic data variation. However, this ideal decomposition doesn't hold in general. We need extra techniques to achieve this. Here we introduce a proposition to enforce this decomposition. This proposition says that if the Lie algebra basis components are commutative to each other, then the corresponding group can be decomposed into one parameter subgroups. Note that this group decomposition is also commutative, and it is where the commutative in the paper title comes from. Furthermore, we also consider a non-disentanglement constraint called Hessian penalty on the group structure, which enforces the impact of a single subgroup in the representation to be independent from other subgroups. Note that this is a stronger constraint than the proposition 1, as the commutative property is implied by this constraint. Now we can start building a concrete model to realize our group-based disentanglement. But before directly imposing the proposed disentanglement constraint on a model, we first introduce a base model called the bottleneck VAE, and it is introduced in the proposition 3. The proposition 3 defines a VAE variant which shares a layer of feature between the encoder and the decoder. In this illustration, it will enforce Z and Z hat to be equal. Our Lie group VAE is a slight variant of the bottleneck VAE, which has a special group feature decoder. Here, the group decoder has changed. By zooming in the group decoder, you can see it faithfully implements the Lie algebra parameterization. Note that the Lie algebra basis AIs are learnable, and the proposition 1 and 2 are implemented as regularizations on the basis. We refer a model with this proposition constraints as commutative Lie group VAE. Here we show the experimental results. We conduct evaluation studies on the disparate dataset. We first check the impact of bottleneck VAE and the matrix exponential mapping. Both components will improve the baseline VAE on disentanglement learning. On the right-hand side, we show how the KL divergence term evolves during training. we can see when the group structure is used, the model can more adaptively learn variations during learning, while the change in other baselines are less drastic. Here are application studies on the group size, the position 1 constraint, and the position 2 constraint. We can see when the group size is large, it is easier for the model to find a solution to represent the decomposed variations. The group hyperparameters for the 2 constraints are around 20 to 40. Here is the state-of-the-art comparison on this price and 3D shaped datasets. Note that the existing state-of-the-art models usually enforce the statistical independence assumption, while our model doesn't do that and it instead leverages the bias of group structure. Here are some qualitative results, and we can see our model can achieve very decent disentanglement results without supervision. Thank you for listening.